All right, so next up, talking about intermolecular forces, aka IMF. So we got 3 main flavors of IMF. Okay, what's the weakest?
Is it dispersion?
Dispersion, also known as London forces. Right? So I'm going to do some very terrible drawing, but hopefully you guys can bear with me. So, sorry, this is number 1. Oops.
Oh, Professor, I can't recall. You know how last time you said the strongest bond was the hydrogen bond, and then it was the second one. Was it dispersion? Was it I can't remember.
A dipole?
Dipole. Like, do we have to list them in order on like our exam?
I don't believe so. But you need to be able to identify which ones are present in a given molecule. Right? So we'll pretend that this is a beautiful picture of an atom. And that the negative represent electrons. Right? So if we have electrons, are sitting still like I've drawn them in real life?
Aren't they in orbit, like they're constantly moving?
They're not in orbit, but they are definitely whizzing around like crazy, right? They are never, ever, ever stopping. So you can imagine that electrons, which all have the same charge, right? Do they want to be near each other?
No.
No, they like to be far away from each other.
Want to be far away as possible, right? But when you're whizzing around really fast, are you always going to be able to avoid a thing that you don't like?
No.
No, exactly, right? So these guys are moving around so much that at some point in time, you can imagine that you might briefly have an arrangement that gets them right next to each other, right? Now, again, that's not going to be something that's going to stick around because they don't want to be next to each other and they're always moving. You guys picking up what I'm laying down? So, but you can imagine that this is possible, right? Not even possible, it happens, right? It's just it's not the most probable arrangement for electrons. You guys still with me? So what this does is it sets up a temporary dipole. How do you spell temporary? I'm terrible.
That's right.
Right, so you have a temporary dipole here, right? Extremely temporary in the most literal sense of the word, that it is fleeting. Does that make sense? So this arrangement of electrons is very energetically costly, right? But it's possible. So these temporary dipoles, molecules get near each other, right? If you have two atoms near each other and you have this atom that has this temporary dipole, right? What's going to have electrons in the nearby atom?
Wouldn't it be on the opposite end?
You're going to try and get away from those extra electrons, right? So you'll actually have them rearrange so that they can get as far away from those other electrons as possible. So what happens is you end up forming an induced dipole.
So it's like a chain reaction, pretty much.
Now, there are only certain conditions under which this can happen, right? So if you have enough pressure, you can make these things, force them close enough together that you can get these induced dipoles, right? So one of the things that we'll talk about in chapter 8 is how these intermolecular forces will lead us into the conversation about different phases of matter, right? So if you put a gas under a lot of pressure, you can turn it into a liquid. Everybody is probably familiar with this from oxygen, right? Especially I think a lot of you guys work in the medical field. So oxygen tanks contain liquid oxygen, right? They're very heavy. And they're extremely dangerous, right? Because they're under a ton of pressure. So once that valve is popped, if there is any fire anywhere nearby, that thing will explode, right? Violently. So what's happening when we take oxygen, which is normally a gas, and compress it until you have these induced dipoles that make the molecules want to stick together, right? Even though they don't normally want to. Does it make sense?
Would that be like condensation or no?
Kind of. Condensation, so that is a process of condensation, yes, I think is what you're saying. So going from a gas, right, to a liquid, this phase change. It would be considered condensation. But condensation doesn't necessarily always have to involve molecules that only have dispersion forces, right? So all molecules have dispersion forces, right? They're the weakest in terms of their strength, right? So when we're talking about intermolecular forces, we care about the strength of the intermolecular force because the strength of the intermolecular force tells us about how sticky the molecules are. Okay. So the stronger they are, the more sticky the molecules are, right? Molecules are not very sticky at all because they only have dispersion forces. Okay. You ready to look at the next one?
Yes.
Questions so far? Is it okay if I erase?
Yes.
All right. So number 2 is called dipole-dipole. And this one is your Goldilocks of intermolecular forces, right? It's your Goldilocks a story that people tell in other countries? Probably not, huh?
What did you say, Professor?
Goldilocks.
No, I only heard it here, not in mine.
No,
No?
no, not that I know of.
With my culturally irrelevant metaphors that I have to stay away from. Okay, dipole-dipole interactions are much stronger than dispersion forces, okay? So when we say that this is the weakest, we really mean it's the weakest, right? Dipole-dipole interactions are much, much stronger, AKA much stickier, right? So dipole interactions are between molecules that are quite sticky. So let's look at a couple examples. So her, so as a reminder, between, right? So we're talking about the forces between molecules, right? Not within a molecule, but between two molecules. So I think it's done. So let's say we have two, right? Everybody comfortable with the fact these are polar molecules. Yes, no, maybe?
Yes.
Yes.
Cool. So who's hogging the electrons?
Oxygen.
Oxygen, right? So if there's more electrons hanging out over here, we know that there's a partial negative over here, partial negative over here, then what must be on the other side?
Partial positive.
And same for this guy. So anytime you have a molecule that's polar, right, there's a tendency for these molecules to orient themselves such that you get these poles. Whoa, sorry, I can do better. Maybe. All right, I can do that. All right. Just trying to make it look more like a molecule. So you can get these molecules lining up such that the positive end of one part is hooking with the negative end of another molecule, right? And so what this does is it forms an interaction between the molecules.
Professor,
Yes.
is there a reason why you rewrote this problem right here? I noticed it's the exact same thing, but then you rewrite it, right?
Yes, because again, we're not talking about the forces that are inside the molecule, right? Polarity would be something that you talk about that is intramolecular, meaning it's inside of the molecule itself. Here, we're actually talking about when you have two molecules, right? How do they interact with, right? Does that make sense?
Yeah, thank you.
So the attraction between the molecules, because of these partial negative and partial positive, read makes them more sticky, right? That stickiness means they are more likely to form liquids or solid, right? And I only do 2 because I'm lazy, right? But you can imagine that there are a ton of these guys in even a very small sample of this, right?
So that's what causes ice also when the water freezes up or cause them. You know how they say like how ice float on top of water sometimes?
How
Or
I
like how ice can float on top of liquid?
yes, let's talk about that in just one. Is everybody this?
Yes.
Any questions? Excellent. So the next example that we have is called
Hydrogen bonding or hydrogen bonds.
Mhm. So this one is actually a subset of these guys. So it's a type of dipole-dipole, right? But it's a really, really strong kind. Okay. So, hydrogen bonds will only occur if you have at least one of the following bonds. Oxygen bonded to hydrogen, nitrogen bonded to hydrogen, fluorine bonded to hydrogen. Okay, so you have to have at least one of these
To have a dipole-dipole interaction.
H bonding meaning hydrogens.
Okay.
So the reason why I kept this example up, the one that we were talking about for dipole-dipole, is because this one is a really common one that causes confusion, right? So does this molecule have hydrogen and oxygen?
Yes.
Yes, but does it have hydrogen bonding?
No.
Why not?
Hydrogen can only have maximum of 2 electrons, is that why?
It's not bonded to the oxygen, it's bonded to carbon.
Exactly. Did everybody understand what Jessica just said? So the hydrogen is bonded to carbon, not to oxygen. See?
Can you ask that question again so I know how she answered it?
Yeah, totally. So I said this molecule has hydrogen and oxygen, okay? But it have hydrogen bonding, because in order to have hydrogen bonding, it's not enough just to have these atoms in a molecule, right? You have to have oxygen bonded to hydrogen,
Okay.
right? Which is not. Is everybody
Okay.
picking up what I'm laying down?
Yes. So it's only hydrogen bonding when it's attached to either O, N, or F.
Exactly. So now let's look at some examples of hydrogen bonders. May I erase these beautiful pictures?
Professor, which one is strongest in those three? OH, NH, and FH?
I would
This
think
one.
it's FH, right?
Oh, I'm yes. Between the three,
Yeah.
hydrogen would be the strongest because
I'm sorry, which one? Breaking out.
hydrogen
You're breaking up.
Oh no.
I think she's saying hydrogen and fluorine.
HF?
Yeah.
Why?
Oh, thank you.
Why?
Fluorine have the highest electronegativity.
That's right. It is very bad at sharing. Am I still breaking up?
No, that was clear.
Okay, so we already looked at one of our hydrogen bonders. Beautiful babe. Water. So imagine drawing such beautiful water molecules, and it's not taking 100 years. So where in this molecule is there a partial negative?
The O.
The O.
Partial
Can-
negative.
Can we talk a little bit about how we know where the partial negative and positive charges go?
So oxygen is more electronegative, so it's going to hoggy face the electrons.
Okay.
Okay. So then that would mean there's partial positives hanging out by each one of these guys. Okay. And same down here. Right. So again, it's just the same story that we were telling with the dipole, right? The dipole-dipole interactions. But in this, it's a particularly strong version of that because hydrogen is teeny, teeny, tiny, right? What is hydrogen made of in terms of its atomic particle?
Did you ask what is it made of?
Yes.
One proton, one neutron, one electron.
Not even one neutron, just a proton with a little old electron hanging around, right? So this is my hydrogen atom with a very ugly positive center, right? And let's say I do my oxygen atom over here. So with a positively charged center. Beautifully drawn electrons. Right. So if oxygen, is that 5? Oh boy, I'm fired. There we go. 6, right? 6 valence electrons. Yeah? Am I nailing it?
No, that's 7.
I was right the first time. I totally thought I didn't. I was like, I didn't draw enough electrons there. Okay, cool. Thank you. 6 electrons, right, for the valence. And if oxygen is really hungry for electrons, what's going to happen to hydrogen's electron?
It's gonna get pulled more towards oxygen.
So what's going to happen is you basically get a situation where hydrogen's electron is pretty much pulled into oxygen, right? So what's left over when hydrogen's electron is pulled in to oxygen?
I don't think there's anything left over, but it's just gonna keep the charge to be a positive.
Mhm. The only thing left is this lonely little proton, right? It's naked. There's no other electrons around it. So oxygen, being the hungry that it is, right, will steal that little old electron, and that makes this almost a far mole charge, right? Not quite, but almost a full charge. And that's why this is such a strong dipole-dipole bond, because this partial negative is very, very strong. This partial positive is very, very strong. Strong as a formal charge, but as close as you can get without being full-on ionic. Does that make sense? Everybody picking up what I'm laying down here?
Yes.
Yes.
Questions? So there was a question Z was asking about the arrangement of ice versus water. And that is a fascinating topic. Actually, believe it or not, a lot of research still happens around why water does what it does. It's a very active area of research in chemistry because water is so important and so ubiquitous. It is something that is very widely studied. So still something we don't completely understand, but that particular phenomena is one that we do understand. So most liquids, they turn into a solid. What happens?
Don't they expand? Like I know water expands when it freezes.
Water does expand, but that's not the norm, right? Most things, when they form a solid,
They
would
shrink.
fall to the bottom of the container, right? They're to the top. I'm trying to think of an example that you guys would have seen, but this is not a process that we see very often. Ice is probably the most common example that you have of going from a liquid to a solid. And all of the other liquids that you're familiar with would be really hard to see. So like,
how about liquid nitrogen?
so liquid nitrogen, I don't know off the top of my head if you can form a solid out of nitrogen, but it would be extremely hard. And I doubt you'd be able to visualize it because you'd have to do it under an incredible pressure, which would mean that you probably couldn't see it. I'm trying to think if there's an example. There are really good examples, and I'm just like not coming with it.
Are you looking for example of an element that causes the same reaction as ice?
No, let me, may I clear this for a second?
Yes.
Cool. I'm gonna look for. You, not that one. It's a cauldron of sorts.
It smells like a bar. It's just good.
Yeah.
So just put it down the side. You can get in a neutral flavor. They don't basically
precise
cut this with
example,
half
but not
dose.
what I'm looking for.
And get a carbonation effect and do it in there.
Oh, that is what they were doing, but it doesn't really count because it's a mixture. Yeah, okay. I guess that's probably the easiest way to imagine it. So what they were doing there in that video was making Campari, which is an alcohol, solid. So when Campari is made, you can essentially freeze the alcohol. Let me see, maybe this one's better than I thought it was. But be quiet, too loud. So this is a solid alcohol, right? I don't know if you can see, it's already forming a liquid on the surface there, right? Alcohols like to be liquids. They don't like solids at room temperature. So that's why it's kind of difficult to answer that question, because it's not something that physically happens easily. So we don't experience it very often, right?
Yeah. I know, because you put alcohol in the freezer, it doesn't ice up.
Yeah, because our freezers aren't cold enough for that.
Yeah.
Yeah, so the freezing point of most alcohols, I think, is like in the negative 50 to 100 degrees Celsius range. So if 0 is freezing point of water, then we're talking about almost to the same amount of space from freezing to boiling that you have for water in the other direction, right? So it's a big jump. So yeah, not something that you just see every day. But that was a very long way of saying that most solids, most liquids, when they form a solid that's more dense. Okay. Water is the exception, not the rule. And it actually has to do with those hydrogen bonds and how that makes the water orient. So when they freeze up, they get less motion, and so they form these crystals, really pretty crystals. You guys have seen that where they make like snowflakes crystallize. You ever seen these videos? I think there was one of those in the one that, oh, maybe that was last semester. This semester.
So does that mean the basically the electrons and the water underneath the ice is still moving in motion the same regular way that it would?
Yeah. See how cool that looks? So you've got liquid water here. And what's happening is the molecules of water are starting to get organized, right? Because they get organized like this, they form a solid, right? That forms these pretty crystals. We live in San Diego, so we don't get to see a lot of ice crystal action here. But if you've lived in a cold place before, a lot of the times when ice storms come through, you'll get these really pretty ice patterns on the windows. So it's very beautiful, but very cold, and I don't like it.
Thank you for answering my question. I don't want to take too much of the class time.
So any other questions about that? Are we feeling more comfortable with intermolecular forces?
Do we need to do any net dipole for exam?
No. So let me just do one more thing. I'm reaching for my whiteboard clearer to clear this. Is it okay if I clear this screen?
Yes.
So
Would you want us to show examples on the exam when it comes up to intermolecular force? Like a drawing or something?
So the kind of question that I would ask you for IMFs would be something like this. Given a molecule, I'm not going to ask you to draw it. I'm going to give you the Lewis structure, and I'm going to ask you what intermolecular force is present in this molecule.
Would
Dispersion.
that be dispersion?
That is exactly right. So this one would be dispersion. Okay. Is everybody comfortable with why? And
Can I ask why is it dispersion?
so, is this a polar molecule?
No.
Mm,
No, it's non-polar.
Comfortable with that, Kaltun?
So, does that mean like non-polars for dispersion?
If you are non-polar, the only thing that you have is dispersion.
Oh, okay. Okay, that makes sense. Thank you.
So, let's look at another example. Bing bong. You guys can't hear the bing bongs. Sounds like a 7-Eleven every time somebody comes in and out of our Zoom room. I thought Magda was going to come hang out with us today.
I know, me too.
I haven't seen her for a while. We only saw her once, right?
She said she was coming, but maybe she was taking a nap. Or she had something better to do.
I think she said she started work or something, because I normally hang out with her for help.
Yeah. Okay, so how about this one?
Dipole-dipole.
So always dispersion forces are present, right?
Oh.
But this one also has dipole-dipole.
So do we answer it for, like, do we put both down for the answer? Okay.
This question asked, yes. If I asked you what the strongest intermolecular force was in this molecule, what would you say?
Carbon and fluorine. Fluorine, actually.
Dipole-dipole, right?
Yeah.
Oh, okay, yeah.
Okay, no worries. Go ahead, Aaliyah.
So would this one be polar because of carbon and fluorine?
Yes, exactly.
Okay, because it's at least one, right? Okay.
Yep. You have one polar at least, and you have asymmetry around carbon. Yes.
Can we go? Why is it the dipole one?
So there's either dipole-dipole or hydrogen bonds, right?
Mm-hmm.
Why is this not hydrogen bonding?
Because it's not bonded with like H and O or F or something, right?
It's not
That's
bonded with
fluorine, no?
oxygen or nitrogen or fluorine.
It has, so it's not enough to just have those atoms in the molecule, right? They have to be bonded to hydrogen. Here,
Okay.
you have fluorine and you have hydrogen, but they're both bonded to carbon, not
Yeah.
each other. Yeah.
Okay, that makes sense. Thank you.
What if fluorine was bonded to hydrogen?
Fluorine is bonded to hydrogen.
It's bonded to carbon, right?
Oh, I'm sorry.
Yes. No, my question was that if fluorine was bonded to hydrogen, that would be then
Yes,
therefore,
that's true. But because hydrogen and fluorine both only need that one extra electron. This is pretty much the only way that you can have hydrogen bonded to fluorine. Right? This is it. It's pretty much the only one. Because fluorine can only bond to one thing. Right? It's definitely not trying to share any more electrons, right? And because it only has the capacity to bond with one other thing, this is pretty much the only time you see hydrogen bonded to fluorine. So if you got this molecule, you would say hydrogen bonds. You could say dipole, dipole, and dispersion, right? Technically, hydrogen bonds are a type of dipole-dipole, so it's implied in saying that it has hydrogen bonds, also has interactions. That makes sense. But I would mark it off if you put all three.
So if I put 3 of those, like let's say you give me this and you tell me, okay, what is the intermolecular force? Unless you ask me what, okay, so I guess I'm confusing myself.
Yes.
If you ask me, what if you ask me what is the strongest? Do I say hydrogen or I still indicate 3 of them?
It would be hydrogen bonding would be the strongest.
Okay.
Calton, what's that?
So I was gonna say, do all molecules have all like dispersion all the time, or is based on the like element?
All molecules and all atoms have dispersion forces.
So it's always like multiple forces.
So that one will be present in everything, right? So if I'm asking what intermolecular forces are present in a molecule, you can always put dispersion forces, right?
Okay.
There's never no intermolecular forces. Does that make sense?
Mm-hmm.
Other questions?
Professor, going back to this over here, I don't know if you can see my arrow, where hydrogen is bonded with carbon. Okay, so here, the reason we determined that it's polar molecule is because that we looked at the lone pairs, right? That's one thing.
Lone pairs are on fluorine. We don't care about this guy. We're talking about this guy.
Then the bond, we saw the bond then, the hydrogen bond.
Symmetric around carbon. You have different attached atoms. Does that make sense?
Yes.
So what about this molecule?
It would be hydrogen bonds.
That'll be hydrogen bonding. That'll be polar. And then polar.
Is everyone comfortable with that?
Yeah, I see that, but I know it's hydrogen bonds because it's like H is bonded to N or H could be bonded to O or F, and it's hydrogen bonds. But then I understand it's dispersion because you said that's everything. But what's like a key indicator? It's dipole-dipole.
Hydrogen bonds are a type of dipole-dipole. They're just the strongest.
Para allá, huevón, y te viene. Echa para allá. Echa para
So
allá.
then,
Vente para acá.
does that mean whenever there's a hydrogen bond, it's all three of them because it's always dispersion forces are always present and hydrogen bonding is a type of dipole-dipole?
Exactly.
So if I put all three on an exam, would that?
That would be totally fine. Yes.
And if I forgot to put dipole-dipole, but I put hydrogen, would that be okay?
Yes, I would probably mark that right.
Okay, and then what would an example be if it's dipole-dipole, but not hydrogen, when it's not HN or F?
So that was the one that we went over in the dipole-dipole original example. That would be one.
Oh, with how it was like the positive attached to the negative side?
For this, right? Which is just dipole-dipole, not hydrogen bond.
Oh, I see, because the H is bonded with the C and the C is bonded with the F. There's no like direct contact with the H and the F.
Exactly. Yes. Everybody okay with those?
So it's dipole-dipole because the F is hogging all of the electrons from carbon.
Exactly.
Okay.
AKA forming a dipole on the molecule. So when you get multiple of these molecules hanging out together, which you almost never have a molecule hanging by itself, right? If you were looking at a cup of water, like literally just a cup of water, it would be, I don't know, something like 10 to the 22 molecules of water, maybe more. But it'd be a lot, right? So 10 to the 22, think about that number. That's a huge, insane, huge number, right? So we're never talking, we talk about when we're doing the Lewis structures, these molecules as though they're individual molecules, but the reality is they're never individual molecules, right? They're always hanging out with other molecules, right? Molecules like to party. They don't want to be alone. Other questions about these?
What is the best way to master on this? Is it like rewatching your lecture and reading the problem? I said, what would be the best way to master on this practice, right?
Yeah, practice problems.
And your lecture, probably.
Testing yourself, right? So taking the practice exam, taking the practice quizzes that are posted, going back through and looking at your quiz and seeing if you could ask yourself, oh, if I was given these molecules, what intermolecular forces would I think they have, right? And then you could ask me.
And then I noticed that chapter 6 has a lot of word problem that has to do with something like finding the molar mass of a molecule, and then
before, I'm going to cut you off really quickly. Maybe get rid of this screen. Is everybody comfortable with that?
So I was wondering if we can have a lot of those on our exam, since this exam includes chapter 6.
I believe there are at least 2. Number 9 on part B. Let's see. Oh, sure. Did I answer your question? I'm sorry, I spaced out.
Yeah, you did actually.
This cutie.
That was like one of the problem that I messed up with, like, finding that if it was polar or non-polar. Actually, you only asked if it was non-polar. And when there's like a lot of those, that's when my brain just blocks,
Yeah, so that's why I say it takes practice, because it's not easy, especially when you have multiple molecules that you're looking at, right? So you have to identify, essentially, in a question like that, you have 4 molecules that you have to identify the polarity for, right? Yeah. Aaliyah, did you have a question? I'm sorry.
I was just gonna say, like, with her question, that the page that you included on chapter 6 for the module, like the key topics and definitions, like, Medina, you can use that because that is really helpful. Like, it makes it so much easier. And then once you do the homework, you can always go back to that, and then you understand like what you're doing.
You're talking about.
Oh, you mean to use the answer key?
Not the answer key, but she includes like the key topics and definitions from that chapter. And then she also gives us examples of how to do it. And it's really helpful.
Okay, thank you.
And the summary, those are really helpful.
Yeah.
I got it. Thank you.
Yeah, I can show you exactly what she's talking about in just a second. But yes, there, I think you're talking about the example and the molar coaster. Yeah. Yeah, that's helpful. Okay, so this problem was one that Z was asking about. So this is a geometry problem. So this is one that I like to give you guys in the lab. I would never give this to you on an exam, but it's helpful in terms of getting you to think about the fact that most biological molecules are bigger than just one central atom, right? So you can think about the central atom as being any atom that you're looking at. What's the shape around it, okay? So this particular problem, what you need to do in order to figure it out is kind of block off all of the other guys here. And we
Crazy, I didn't even see the one by the N.
So does that make sense now?
Yeah.
So you pretending like whatever the rest of the molecule is, it's just one attached atom, right? And so you have 3 attached atoms, 1 lone pair. So what's the geometry there?
Would that be trigonal pyramid?
Trigonal pyramid.
Exactly, you got it. Does that make sense?
Yeah.
Yes.
When all else fails, Zoom. All right. Any other questions about that? Because I would love to spend some more time with other chapters.
You said there's no way you're gonna give us that for exam, right?
No, I would not.
For the lab. Okay.
I understand 9 on that lab, but I just wanted to make sure I got some other ones right on that.
Okay, but let's talk about that another time, because I think that it would be more valuable for us to use this time to talk about questions from chapters that we're definitely not spending as much time with. Yes?
And then Professor, I couldn't actually find, or maybe like the other students can answer this for me, you know, who might have watched it already. I could not find the chapter 8.1's lecture.
It's in chapter 4.
Yes.
Chapter 4, okay.
Yes.
It's like a small section.
It says chapter 4/8.1, which means that they're both stuck in there.
We did some problems on the chapter 4 homework too for it.